Hey everyone, in this video lesson, we are going to learn about repeated sampling. To get started, we're going to do a little bit of a warm-up based on what we learned last lesson, confidence intervals. So the Canadian Commercial Pilot Written Exam is written by thousands of people each year. Last year, at a local community college, 25 people wrote the test and had a mean mark of 82% between them. So is that 82% representative of the thousands of people that written? We're going to find a 99% confidence interval, so we can say, hey, the average score for the thousands of people that write it each year is within this and this, and we're confident that's true 99% of the time, or 99 times out of 100. So to do that, yesterday, or last lesson, we found the margin of error using this formula. The margin of error was the Z score corresponding to our confidence level times the root of P times 1 minus P, and P is the proportion we're using in this question. Here, our P is 0.82, 82%, divided by N. So the bigger N, the more people in your sample, the smaller the margin of error will be. And so let's try this. And I should say too, you can try all these questions yourself, see how you did from our previous day, and then unpause when you're ready, or you can follow along with me right now. But for 99% confidence level, we used a Z score of 2.576. And we spent some time in our last lesson showing where that number came from. Our P is 0.82. 1 minus that would be 0.18. And our 25 candidates. So let's see, will that answer be, will that mean 82% be accurate within 5%, within 2%? I don't know, let's see. So 0.82 times 0.18 divided by 25 square root times 2.576. So to 3 decimal places, I got 0.198 or 19.8%. The margin of error is 19.8%. That's pretty big. That means that to be 99% sure of what the actual average is, we'd have to say it's like, well, that's actually, we'll go into part B. So our margin of error was 19.8%, 0.198 or 19.8%. So our confidence level for the exam marks is 82% plus or minus the margin of error. In terms of an interval, if you do 82 minus 19.8, you get 62.2. And 82 plus 19.8, 101.8. So we should be able to calculate a margin of error, create a confidence interval. This is the 99% confidence interval, I should say too. And be able to complete a statement like the following. So in general, the mean written mark on the exam is 82%. That's what we got by having our 25 people write it. This is accurate within 19.8%. And because it was a 99% confidence level, this is accurate 99 times out of 100. And then we just showed the mean mark is between, the highest value is 101.8, and the lowest value was 62.2. Now, you may be thinking, well, you can't have a mark over 100%. And the reason we got such a wide range of values is because, thousands of people are writing this test, and you only sampled 25 of them. So if you wanted to draw some general conclusions and be 99% confident of your conclusions, you're going to have a very, very broad range of values, which is why we got from like 62 to basically perfect. So it's not really very helpful. If we wanted to have a smaller margin of error, we'd have to sample more people who wrote the tests, maybe go to a couple other community colleges and get their results too. The last thing we should be able to do after our previous lesson was to use the margin of error formula and find a sample size. So if you recall yesterday, we took our margin of error, last day I should say, we took our margin of error formula and we rearranged it. You should probably know how to rearrange this formula, but I can do that. It's a pretty quick derivation. Square both sides. P1 minus P. Guess I didn't need that big bracket there. I might erase that. So squaring both sides, you square E, you square Z, and squaring a square root kind of basically undoes the square root. And then to get n by itself, we're simply multiplying up by n and then dividing by E squared. Z squared times P times 1 minus P all over E squared. What do we get for this problem? So for a 95% confidence level, the Z score we used was, double check this too, 1.96. So 1.96 squared. Our P was, in this case, 0.84, making 1 minus P 16% or 0.16. And the margin of error was 3.5%. So 0.035. Don't forget to square it. So you can see the different study got a different mean score, but a much smaller margin of error. So we're expecting to see, I know it was a different confidence level, we're expecting to see probably a much larger sample size than the 25. So 1.96 squared times 0.84 times 0.16 divided by 0.035 squared. So about 421 students or candidates. So you can see, to get that margin of error down, to get a better confidence interval, you just have to study more people. So that's what that kind of illustrates there. All right, so let's move on to today's topic, repeated sampling. So let's say you're trying to measure a characteristic of a population. So maybe, I don't know, how fast people can type, how many words per minute people can type. It'd be impossible to go to every single person who uses a computer and measure how fast they can type, how many words per minute they can do. Instead, what we would do is we would take a sample. You might go sample 10 of your friends and see how fast they can type. To be even more accurate, you might take those 10 friends, find a different group of 10 friends and find their average, and then average those two averages. Or you could even go another group of friends and another group of 10 friends. And you can keep sampling groups of 10 people, see how fast they type, and average those values out. This is the idea behind repeated sampling. You take samples over and over and over again and estimate the mean of a population that way. So repeated sampling is when samples of the same size are repeatedly taken from a population that follows a normal distribution. So what happens is, so here's your population, and it's normally distributed, and it has some mean mu with some standard deviation sigma. So when you take samples, sometimes your mean might be a bit lower. Sometimes the sample mean you get might be a bit higher, sometimes pretty high, sometimes low, sometimes maybe right on. But the idea is the average, these sample means that you collect are going to be normally distributed too. It will have kind of like a mean of them. Some will be lower, some will be higher. And what you get is, when you take all these sample means you get a distribution where the average of the sample means should be the actual mean. But because these guys are so close to what the true population mean is, the standard deviation of these sample means you get is going to be really small. And it's actually related to sigma in the following way. The standard deviation of those sample means is sigma divided by the root of n. So for example, if you did a sample mean 4 times, the root of 4 is 2, and your standard deviation would be cut in half, right? So the means of the samples will be normally distributed with a mean of mu. So again, in theory, when you take a bunch of samples and find the means of those samples and then find those at the average of those means, in theory, it should be the population mean. So that's where we get the mean of mu. And in theory, we should get of all those sample means we get, they should be a lot more tightly packed together than the actual population. So the standard deviation will be smaller too. The mean of mu and standard deviation of, and we give this a fancy name. We say sigma with the subscript x bar to say that's the standard deviation of the sample means. It's population standard deviation divided by the root of n. So this guy here is the standard deviation of the sample means. And this guy here is the standard deviation of the population. N is the number of samples. All right, so just a quick note there. By taking more sample means, your estimate should get closer to the true mean, right? Like if you wanted to really measure people's typing speed, you wouldn't just do one group of 10 people, maybe not even 2, maybe 3. If you took 10 samples of 10 people or 50 samples of 10 people, the more you sample, the better your estimate's going to be. And that's what shows up here in this dividing by root n. The more samples you do, the tighter this is going to be, this distribution of sample means will be. Before we get into an example, let's talk about confidence intervals for sample means. So here's the idea. So let's say you do your study on getting the words per minute, typing speed. You take a bunch of samples, you find their averages, and you get a value. So you might say, well, based on all these samples I got, maybe the average typing speed is 30 words per minute. Just like last day, we would like to be able to say, well, how confident can I be that the population's words per minute is around 30? Can we give some kind of interval where we're so sure that the actual value lies between that value? We can. The margin of error for cases like this with sample means. So this is a different case. So we'll use a different formula. It's different than when we were doing a margin of error for some percentage. Here it's a margin of error for like a sample mean. You get it by doing this. It's simply Z, the Z score you want. So again, it would be different depending on whether you want a 90, 95, or 99% confidence interval. You look up our 3 values times the standard deviation of the sample means. Or if you prefer, since we talked about earlier, the standard deviation of those sample means will be sigma divided by root n. So this is the standard. We also call this the standard error, if you see that in some resource. So let's do an example. You're going to see or a couple of examples. You're going to see this isn't actually too bad. So I think I missed an example to do with you guys actually. So let us Yeah, I think I can improvise this on the fly. So you guys had a question. So you know what we're gonna do? This is okay because this is it's COVID-19. We're at home. We are doing all the best we can. I'm actually going to just pop this back in. Yeah, I didn't pop in that example. So let us duplicate, delete that. And we'll insert this example. Yeah, there's definitely no way I'm restarting this video. That's okay. It's okay. All right. So here we go from current slide. All right, let's get this example done. So yeah, flip back to the front to the previous page, guys. Sorry about that. So we're not using the margin of error in this question. We're just talking about this idea of when we do repeated samples, the sample means get really tightly clustered together. So here we have the tires on a rental car fleet have lifetimes that are normally distributed with a mean life of 64,000 kilometers and a standard deviation of 4,800 kilometers. So these values you can assume they've got from this rental car company, like the tires they use, years of study. This is what the manufacturer's data tells them. This is the population mean and the population standard deviation. Now, Mechanic checks all 4 tires on 10 randomly selected cars. So we should note that that's 40 tires. N equals 40. What are the mean and standard deviation of these samples? So let me just switch to a better color here. And what I want to say here actually too maybe is what should be. Because it's unlikely if this Mechanic checks 40 tires for the lifetime, it's unlikely the mean will be exactly 64,000 kilometers. But the idea is that if he checks the lifetime on all these 40 tires, then the mean, it should be 64,000. Should be the same as mu. That's what it should be. But what he's going to find is if he took the standard deviation of these 40 samples, what he should find is that he gets a lower standard deviation. They're more tightly clustered together. We take the standard deviation from the original, 4,800, and divide it by the root of n, the root of 40. So instead of having a standard deviation of 4,800, over 40, it's much less. I'm going to say about 700. You know what? It's actually pretty close to 759. So these 40 lifetimes he'd get would be, much tightly clustered together. And so let's imagine this Mechanic is checking the lifetimes. The manufacturer says the lifetime is 64,000. How likely is it that he selects 40 tires and the sample mean is 62,500 or less? And maybe we could think, oh, you know what? Maybe they're kind of pulling our leg here. Maybe this life they're giving us, maybe they're overinflating it. Well, we can check this out. So this is actually a normal distribution problem that should be pretty pro at by now. The mean is 64,000. And we've been asked to find the probability that this Mechanic samples 40 tires and the mean is less than 62,500. So the way we normally do that is to find a z-score. So we know the z-score here will be negative 62,500 minus 64,000 all over, and our standard deviation here is 759 we're using. 100 minus 64,000 59. It's about negative 1.98. And then however you want to show this, I'll show a lot of work here. What's the probability that our sample mean is less than 62,500? This is the same as probability that the z-score is less than negative 1.98, which we can look up directly from our tables. So negative 1.98, 0.0239. So it's pretty unlikely that he's going to get these 40 tires and they'll be less than 62,500. It's around 2%. Having done that example, we have talked about the standard error. And now we can go on to this example here. So let's say we have an agricultural fair. We got 8 giant pumpkins entered into a contest, and there are the 8 masses right there. Results from past fairs, I guess should have an S on the end, suggest that the masses are normally distributed with a mean of 14.2 kilograms and a standard deviation of 2.5 kilograms. So let's find the mean of this sample. So let's find of the samples. Jeez Louise, should be necessary too. And the standard deviation of the sample means. And then we'll find a 90% confidence interval for the sample mean. Then we'll have a little conversation about it. So the mean of the samples, we're just adding those guys up. So 11 plus 13 plus 15 plus 18 plus 12 plus 14 plus 10 plus 16. So I got 109 divided by 8 pumpkins. About 13. I'll just round it to about 13.6. And we know that these sample means should have a sample standard deviation, sigma x bar of sigma over the root of n. That is 2.5 divided by the root of 8. 2.5 divided by root 8. About 0.88. Let's just call that 0.9. All right. So let's say we had these values, and we for these pumpkins, and we wanted to say, how confident could we be that the masses of all these giant pumpkins are going to be, or what range of values can we be 90% sure that these masses fall between? So we can do that here by finding our margin of error. Margin of error here, the formula is a lot easier. It's just Z times sigma x bar. And we want a 90% confidence interval. So for this question, our Z we've been using 1.645 times 0.9. And we get about 1.5. All right, so we've got part A done. And now we're ready. This is into part B. So now we can say our 90% confidence interval. Is 13.6 kilograms plus or minus 1.5. And that we can do with mental math. That's 12.1 kilograms to 15.1 kilograms. So we can be 90% confident that the average of all giant pumpkins would be between 12.1 and 15.1 kilograms. So yeah, it's just a little new formula for margin of error, calculating this the standard deviation of the sample means is pretty simple. You do the population standard deviation divided by the root of n. Why don't you guys give this a try? So in this question, we have some light bulbs being tested, because a lot of times on the box of light bulbs, it might advertise, hey, we last so much longer than our competitors. Here, the manufacturer claims these light bulbs last an average of 1,200 hours, and the standard deviation is 420 hours. So we're basically just kind of seeing, hey, does this hold water? Let's actually test some light bulbs. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 light bulbs. So you guys find the mean of those samples. We've got our n value, so we'll be able to find that standard deviation of the sample means pretty quickly. I'll maybe do that first, actually. So sigma x bar is just sigma over root n. I think I counted 12. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 12. So that would be 420 divided by the root of 12. About 121, we'll say. And what do we get when we average these 12 values? So 998 plus 1, 2, 3, 4 plus 1, 5, 2, 3 plus 1, 7, 6, 0 plus 937 plus 1, 1, 9, 3 plus 9, 9, 6 plus 1, 0, 0, 2 plus 986 plus 1, 2, 8, 5 plus 1, 1, 6, 3 plus 1, 7, 1, 6. Hopefully you did it yourself and you fast forwarded through that. And we'll divide that by 12. So I got about 1,233. And this is in hours. All right, and our 99% confidence interval. So for 99%, we are using Z equals 2.576. So we'll calculate our standard error. So that'll be our Z times sigma x bar, 2.576 times 121. So that is about 312. That'd be 312 hours. All right, so our 99% confidence interval, we can say is 1,233 hours plus or minus 312 hours. Or you can state that as an actual interval. So if you do 1, 1, 2, 3, 3 minus 3, 1, 2, 921 to 1, 2, 3, 3 plus 312, 1545. So what does this tell us? So let's say you're this consumer group and you wanted to test their claim that these light bulbs last 1,200 hours. Just from measuring these 12, you could say, hey, we're 99% certain that the average lifetime of these light bulbs will be between 921 and 1,545. The manufacturer's claim of 1,200 lies smack down in that interval. So it appears like their claim checks out. So what you guys should be able to do after today is basically just something like this. So given some kind of batch or sample, can you guys calculate the standard error, the average of the sample means, and can you use it to create a confidence interval? So pretty much if you can do this with a specific confidence level, you're in good shape for today. It's really one kind of specific type of question, but instead of tying into the last lesson, I just wanted to give it its own lesson and just spend some extra time on it. So next steps for you guys. The PDF of practice I have on Brightspace. has some practice from today's stuff and our previous lesson stuff. So you can give any of those a try. As usual, please let me know if you need anything, and we'll see you soon.